Welcome to the Unit 5 test questions video. This video will have the explanations for numbers 1 through 8. Question 1. To answer question 1, you should have used an antiderivative. Although you may have recognized that cosine and sine have this easy pattern, that rule for area really only works when you're going from 0 to pi or when you're cutting that in half. So going from 0 to pi over 4, you can't necessarily use the area 2 that we like to use. But the antiderivative is pretty easy. Notice that I evaluated using the unit circle. Go ahead and use the same strategy to work out this question. And just like before, you should have used an antiderivative, so the correct answer was C. And you can see my work here. Ignore that typo. And this is just a 1. Notice that for my last step, I just combined these into one term to get e to the 8th minus 1 over 4. And that's why the answer was C, which is what you see right here. Question number 2. Question number 2 was kind of an overlapping areas problem. I like to draw myself a little diagram, although some of you can probably do this in your head at this point. But imagine we have some function. I usually just draw a curvy line knowing that this is not necessarily what it looks like. Each of these integrals represents a certain area. So from -1 to 0, the area in this little section is 5, and I just mark that area. From 0 to 4, which is from here to there, the area is 7, and from 1 to 4, right here to here, the area is 4. The area we're looking for is from 0 to 1, so I've shaded it in. And in order to figure out this area, I see, based on my diagram, that I could just take 7 and subtract 4, and it turns out the 5 actually wasn't even relevant. Notice, again, that this is not necessarily what f looks like. It's just a tool to help myself think about what they're saying. Use that same strategy, or any strategy you know, to solve this one. And the correct answer was A, as you saw in Edpuzzle. Again, I thought about the overlapping areas. I labeled each of the intervals they told me, and I realized that this area they're looking for is from -2 to 3, which would be adding 6, and then this area right here. Now, this is a little bit weird maybe because of the negative. In reality, this function would have to be under the graph here to make this area negative. But again, I'm not really relying on the function. I'm just kind of reasoning out that whatever the graph looks like, this second half of the section I'm looking for has to be the total amount minus this amount right here. So I did 5 minus -2. And again, the area, the actual function doesn't really matter. It's just the idea of taking the whole area and subtracting whatever area is in this area. And then you get that part and add it to 6. Question number 3. Question number 3 was the right-hand approximation method. I find it helpful, at least when we're talking about a function that I'm really familiar with, to sketch a graph. You don't have to sketch the graph. What you do really have to be confident with, and again, this work on the side is for number 4, so ignore that. I'm just looking right here. What you do have to really be confident with is the partition, which is those x values. So of course you need the width first, which is going to be pi over 4 because I'm dividing pi into 4 rectangles. And then these numbers on the inside are the outputs, or the y values, of a special set of x values. Since it's the right-hand approximation method, I'm going to ignore 0 and use the right-hand endpoints, but I don't just use those values. So if you chose E, your mistake was you forgot to take the height. You just used the x values. When you plug them into the sine function, which you can do using a unit circle or just by knowing your graph, A is the correct answer. Use the similar strategy to work out this one. So the correct answer here is E, and I'll let you look at it here before I show you the explanation so you can just confirm. And the reason is your delta x is going to be 1/2. You're going from 2 to 5, and you want 6 rectangles, so I divide them all in half. And I find it helpful to use fraction form because then it's easier to square them. And I just did one of the calculations out so you can see it. The first x value I'm going to use, since it's a right-hand Riemann approximation, is 5 over 2, in other words, 2.5. Well, if I take 5 over 2 and I plug it into 1 over x squared, that's the same thing as taking the reciprocal and squaring it. Just keep, change, flip if you're uncomfortable there. When you square the reciprocal, you get 4 over 25, and that's the y value for the first rectangle. You could repeat the same process. Each time you're basically taking the reciprocal and squaring it, which is why you get E as your correct answer. Question number 4. Question number 4 was asking for the average value of a function, so you needed to remember the average value formula. If you don't have this memorized, this is just memorization. Notice that f of t, and when you use this formula, is the exact function whose average you want to find. It's not the derivative of it, it's not the antiderivative of it. This function is this function. 1 over b minus a is like dividing by the width. You've got area divided by width gives you height, and we want average height. Implementing the function, implementing the formula, you just need to be careful with your fractions. Notice I took an antiderivative. I evaluated at 3 and 1. Very common mistake when you do this is to forget that you need parentheses around the second evaluation. So some of you may have forgotten that this -1 is going to turn into a +1 in that situation. I went ahead and subtracted right away instead of dealing with the pluses and the minuses. And then you just have some fraction skills. 1/3 and 1/3 is 2/3. 36 minus 2/3 is 35 and 1/3. And then I converted that to a fraction. Go ahead and use the same strategy to find this average value. The correct answer is A, which is -161 over 4, and this is what the work looks like. Question number 5. In 5, you had to combine some of the biggest concepts we've ever done, although the actual work isn't too hard if you did know the concepts. The first concept was the fundamental theorem of calculus, which says if you take the derivative of a function that's defined using an integral, so this g of x's output is the area under this curve. In other words, it's defined using an integral. If I take the derivative of that function, then the derivative just equals the inside function, the function underneath the integral. You guys may think of that as just plugging in the x, which is fine, but not very deep. So according to the fundamental theorem of calculus, g prime of x is just x squared minus 4. So if we know the derivative and we're looking for a maximum, we can use the first derivative test. This is my derivative function. I set it equal to 0 and solve for x, and of course that's an easy one to do in your head. It's just 2 and -2. And then I set up my number line. Remember, don't get confused because we've done integrals now. First derivative test, you plug in values in between the critical points into the first derivative. So when I plug in a number less than -2, this term turns into a positive and it's larger than -4, so the answer is positive, etc., etc. What makes something a maximum? A maximum is when the graph switches from increasing to decreasing, which means -2 was the maximum. I'll put an example problem just like this in Edpuzzle if you want to try it. Question number 6. In some ways, question 6 is really testing everything you learned before you got to calculus. In Algebra 2, you learned how to graph an absolute value function. This is a normal V-shaped absolute value function shifted to the right 2 units. There's my sketch. The area from 0 to 2 is a triangle, and in geometry you learned that the area of a triangle is 1/2 base times height. I saw a lot of people in the free response section somehow forget to multiply times the 1/2, so just double check that you're doing that. I'll put another one just like this in Edpuzzle if you want to try it yourself. Question number 7. In question 7, the variables kind of give you the illusion that this is a difficult question, but it's actually one of the simpler problems. You just have to remember all your properties of integrals. Remember, if you have an integral of 2 functions that are added together, you're welcome to split that into the integral of the first thing plus the integral of the second thing. And I'd be willing to bet most people made the mistake of just saying this was the integral from a to b of f of t plus 3, forgetting that 3 is a function as well. It's a constant function. So you did need to take the integral of 3. There's two ways to think about taking the integral of 3. You could think of it just like a function and take the antiderivative, which would be 3x, and then you would plug in b and a. Or I prefer to think of this like a rectangular area. Imagine your graph here, you're going from a to b, and then you've got a line 3 high. That area is going to be 3 times b minus a, which is the width. And then, of course, the first integral they just tell you is a plus 3, and then it's just baby algebra, combining like terms. That's why it was a. I'll put another one like this in Edpuzzle if you want to try it yourself. Question number 8. More than anything, I think question 8 required confidence and persistence, which at the end of a section you're racing for time, I get it, maybe this was a challenge. But see if you can put it together now. So looking at the format of this expression, we've got a number out front and then a bunch of things being added together. Knowing what Riemann sums look like, the number out front, I know, represents the delta x, in other words, the width of each of these rectangles. And then I also know that the number of rectangles, or n, should correspond to the number of terms inside parentheses. So although I can't exactly count them because of this dot, 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 I can kind of look at what's happening and figure out how many rectangles there are. If I go from 1/10 to 2/10 to 3/10 to 4/10, dot, 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 all the way to 10/10, it should be pretty obvious to you that there are 10 terms inside. They're just counting 1, 2, 3, 4, 5, 6, all the way to 10. So I know that n equals 10. I've got 10 rectangles, and I know that the length of each rectangle is 1 over 10. If you multiply the width of each rectangle times the number of rectangles, the total length of the interval has to be 1, because if you add up 1/10 and 2/10 and 3/10, etc. Now, technically, with that much analysis, we could be talking about an interval of 1 going from 1 to 2, or 5 to 6, or 8 to 9. It would all depend on what x values are here. But the nice thing about a multiple choice test is you can actually just look, and as soon as you realize that the total length involved has to be 1, you can eliminate a and d. From there, we're comparing c and b. Now, the difference between these two is that this is an average value formula because it has a fraction in front of the integral, whereas this integral is just the area under a curve, and that's what Riemann sums are for, which is why it's c. If you want to go a little farther, you can actually map out what the x values should be going from 0 to 1, counting by 1/10, 1/10, 2/10, 3/10, and then you can figure out what the function's doing to each of those numbers is it's squaring them. You can see that right here. So the x squared is the function. I'll put one more like this in Edpuzzle for you. Otherwise, you're done with this section of the test.